Okay, so hello everyone. So I will present you a case of a large-scale network who has been simulated in the EMTP. So I will discuss about challenges and the solution we can have with the such large-scale modeling. So we know all of us that we need to do some interaction studies between power electronics who will be integrated to the grid for renewables or for interconnections. So for these interaction studies, we need electromagnetic transient simulation, and we want to apply it to a large-scale network. So what are the challenges? The first challenge is how we can modelize such large-scale network. Doing by hands and retrieving the data is quite challenging. And also because we will have a large-scale network, we will have a huge computation. So here in this presentation, I want to describe some solutions. One part of the solution will be on the data and how we modelize the network. In this case, was in the EMTP. And also, I will discuss some research area on sparse solution techniques who can speed up the solution on one core and several cores. So all the work was presented here have been published in a Stigray paper, who has been also presented 3 weeks ago in Trodai. So here I will introduce the case. So this case is a French grid with all voltage level we have in the grid. So from 400 kV until 63 kV. So of course, I can admit that this network will not be used in studies, but part of this network can be used in studies. But the objective here is to demonstrate that even if we have all the data, all the network data in the EMTP, we are able to simulate it in reasonable times. So here I will make a short description of what we have on this network. So we will have, so in terms of nodes, so I speak about three-phase nodes, is 25,000 nodes. So here is the size of the main system of equation. So we have included saturation on every transformer, and we have put all synchronous machines and their control. So for synchronous machine in France is power meter, power plant, hydraulics, and some thermal plants. And of course, some HVDC links has been included, so we have 7 interconnections. We use here the generic modeling. So here, how we can modelize this network in EMTP and how we can improve the computation time. So here's the picture. Yeah. Here's the picture. Here is how the network looks like in EMTP. So how we can draw all this network in EMTP. Of course, we don't have it. We didn't it by hand. So I will detail how we can retrieve it automatically or redraw all the network. So this is the outline of the presentation. So the first part will be dedicated on how we imported all the data in EMTP. So we use an automatic EMT interface, and how we can we manage to have some visualization of the modeling I presented before. Then the second part will be on the sparse solution techniques. I will explain how we can accelerate the simulation. And lastly, I will present some simulation performance. So this is a whole picture of how it looks like the automatic EMT interface. So on the left, we have how the network looks like in our planning tool data. We consider that our planning tool data is the referential database of the network data. So it's mostly used for planning and post-event analysis. So what we do is that on this planning tool, we have a feature which exports SIM files. So it's XML files. And then with this XML file, we import it in EMTP and we draw all the data. So here I go deeper into the workflow of the SIM-EMT interface. So we start with the planning tools there. So we have the SIM export here. You can see that you have another path workflow. because some data are not present in the SIM standard, or maybe are not exported from the planning tool. So you have to do some additional CSV files to import this data. So here I give some example from your frequencies, the coordinates of electrical substation or machine reactors. So then you have the XML files, then you can go to the SIM models, and then we use the EMTP models, we use the COM interface to redraw automatically all the modeling. Then we arrive at the empty secrets. So here I will talk about how we visualize the modeling how we can visualize the modeling. So here we have two methods. So here we have the visualization in the planning tool. So we have first methods based on the already known coordinates of the French database. So here we can redraw the French shape. But of course, if you don't know any coordinates, we can have an automatic layout, which is not user-friendly compared to the French database layout. So how automatic layout works? So the idea is to represent the network as a graph. So each node will be a substation, and a line will be an edge between each node. So when we have this graph representation, we feed an algorithm from Microsoft Automatic Graph Layout. So this algorithm will connect or put the nodes proximity, and also it will minimize the crossing of edge of a node to increase the visibility of the modeling. Other solution was because we want to have the shape of France, we don't have to be more to gain visibility. So we use the French database layout. The problem is with this pre-existing coordinates is that we are in the planning tool. So in the planning tool, we are imagining some network development on already not there. So we have some coordinates who are not present in the database. So here is the whole picture of the algorithm. It's just to positioning unknown substation near to the closest known coordinates. So with this French database layout and with this automatic repositioning of unknown coordinates, we are able to redraw the whole network with the French step. Okay. So now we have the solution for the modeling of the network. So we have imported, we have a nice visualization of the modeling in EMTP. So now how we can speed up the whole solution of the 25,000 nodes. So here is a recap of which part of the EMT solution takes times. So basically, when you have a network in EMT, we'll do some discretization, and in each time step, you have to solve a linear system, iterative, because you have to update this linear system accordingly to the setting point of non-linear devices. So when you start this linear system, you have several steps which use some LU decomposition, and then you use forward and backward substitution. So this step is quite fast when you know the LU factors. The most expensive step is this one, and we need this to refactorize the matrix when you have some update in A, which come from the nonlinear elements. So what has been done in EMTP is to use a modified version of LU solver, KLU solver, and to put parallelization and partial refactorization. So I will go into several slides. On the upcoming slides, I will explain the two concepts. So the first concept based on parallelization is quite simple. The idea is to put the matrix A in a diagonal form. And because each matrix is independent, you can solve it independently. You can do the value decomposition and so on. Why we have this diagonal form? Because in the network, you have transmission line decoupling. I mean, when you have transmission line decoupling, we'll have some, you have decoupled networks, so you have some historical source currents, and it's completely decoupled, so it's topologically separated. So here I will explain what is what we do in the refactorization. So the first step was is just reordering the matrix just to minimize the filling of the value factor, because you have less non-zero in value factor means you will be more efficient. So the factorization is left of clean. So here is your Euler factor, and you from the left to the right you refactorize each columns. So here I talk about factorization. So factorization will do it clear of the simulation. And then you have the value factors. When A is updated, you have to do refactorization. So here, just here, here you have another element, pivot. When you select the pivot, you do some permutation there. You have to select the pivot here. And this takes time. But when you do refactorization, you can admit that this step can be, it's not necessary, and you don't have to redo some permutation. This is the next step. When you call it refactorization, it means that you only refactorize numerically the value factors. So here you start from you have the same algorithm, but you don't have the pivot selection, you keep the pivot, and you just redo the computation of the column. So here I put C, it's the set of columns you have to recompute. So in the original Kaiju solver, what they did is that they recompute all the columns. So it's not so efficient. That's why in the modified Kaiju version, we say that, of course, maybe we don't need to recompute all the columns. Maybe we can start from the column, the minimum index of column who have changed in A. So that we did. So we can compute the minimum column to have changed, and then we compute only a subset of columns, and so we can increase the simulation time. So this is the last step what we applied for the simulation of the French grid. It's about how we can combine BTF and partial refactorization. Remember, BTF can be used for parallelization, but also it can be used to speed up the partial refactorization without parallelization. So imagine you have a matrix there. So you have the diagonal form. You don't want to parallelize, you want to run it on one core. But you can use the BTF transform just to speed up the computation of value factors. For instance, if you have only this matrix have changed, so we go on this submatrix, and then we compute the minimum index of columns who have changed, and then we compute only this column. So to compare to if we don't have this technique, but we will save in time because you don't need to recompute all the columns of the original matrix, but you compute a subset of a submatrix, a subset of columns of the submatrix. So these techniques will speed up the simulation on one. Okay. So I present a solution to improve the computation time. So now we want to know what things are going on when we run simulation in EMTP. So here, so you put the modeling we have in EMTP, and then I present here are the performance we have in the actual version of EMTP. So first, for the load flow is quite fast in terms of iteration. 7 iterations just converge. The execution time is not so high. And also for the time domain simulation, so we do 1 second and 50 microseconds. And in total, 1 second is 47 minutes. So it's not so huge. You can see here how we have the iteration for the nonlinear elements. So actually, with the actual solver, the simulation of this network doesn't take a lot of time. It's only 1 second and 47 minutes. And it's, for us, like in terms of complexity, the upper bound of networks. So if you look on the detail of the solution of this network, is an interesting thing is that the solution of the linear system here, iteratively, takes a major part of the network because you have a lot of nodes, and a small part are the control, and the other part are the data of historical tables. So here, we saw that the solution of the linear system takes most of the computation time. So maybe the techniques I've explained before can help us to save time. Okay, so here are a recap of the techniques I explained. So legacy is the current solver. MKU is modify KU solver. We use a faster refactorization and parallelization. And then you have the refact PTF, the technique when you use the PTF only to accelerate the refactorization and not for parallelization purpose. And we can combine them with parallelization. So here are the simulation results. So I put here are the speedups. So you can see that on one, just changing the solver and just applying refact PTF, you almost have a speedup of 3.8. It's quite only on one core. So on one core, we have almost divided the simulation time by 4, just applying efficient sparse techniques. And we can use also parallelization. So here I have to precise that parallelization will be applied only on the solution of the linear system. So for instance, for the controller solver or update of historical terms is not parallelized, it's sequential. So with the parallelization, we can also improve the performance until 5.7 speed. So in total, 1 second here takes 8 minutes, compared to the previous figure when 1 second takes 47 minutes. So here is the conclusion. So building such a large network, yes, it's challenging, but you have solutions for the modeling. If you have a referential database, like Earth, we have a planning tool, you can use the C import of the data, and then you can rebuild all the network automatically in a EMT simulation software. You have solution to improve the performance on one core or by using the parallelization. In this case, you have proof that only these techniques can have improved like almost by 6, just divided by 6 the computation time. For instance, for the French grid, 1 second is simulated in 8 minutes. So here are the further works. So here, what I've been presented is that the developed version of EMTPs is not yet integrated in the commercial version, but I hope it will be integrated in the future. Regarding the modeling, we can add also offshore wind parks and manufacturer model to the French grid modeling. And here we can also combine the parallelization we choose here with the co-simulation platform. When you use validation with the co-simulation platform, in this case, we parallelize all the network and solution. Thank you for presentation. If you have any question.